One of the most important proofs in mathematics is that the square root of 2 is irrational. Now, this proof isn't just important, I feel, for mathematicians, but it's also important for philosophers because this is a great way of introducing a certain way of thinking. It is super important for scientists. It introduces another way of thinking for them as well, and for the average person. Hang on a minute. The thumbnail mentioned someone died for this. Well, where's the body? Now, the murder actually didn't happen in recent memory. The murder I'm talking about happened potentially sometime around 500 BC. Now, why do I say potentially? Because he didn't really die for proving this. Although there's some belief in some exaggerated version of history where that is the case of what happened. Now, what am I talking about? I'm, of course, talking about the man who proved or discovered irrational numbers, and that is going to be Hippasus. Now, who was Hippasus? Well, at around 500 BC, Hippasus was a member of a religious community called the Pythagorean Brotherhood, founded by, you'll never guess, Pythagoras. In short, these Pythagoreans believed that all numbers can be expressed as a ratio or as rational numbers. All numbers can be written as a over b, where a and b are integers. And our hero Hippasus, while he was studying with these members, realized that, hey, and we don't know how he came to this conclusion. So a lot of people think, and I think this is reasonable to assume, that he was likely looking at the triangle of the two sides equal to 1 and figuring out that this hypotenuse was the square root of 2. And when he was looking at this, he probably figured out that it's really difficult to come up with a ratio of a and b that is going to equal to the square root of 2. So when he proclaimed to his colleagues that there do exist numbers that cannot be expressed as this, there do exist numbers that are not rational, a lot of them were shocked and a lot of them weren't very happy. Again, this was a religious community. They had religious activities, they had fasts, they had diets, they had maybe even sacrifices we don't even know about. But they very strongly believed in math, religion, philosophy, and all these sorts of things. So when someone comes along and says, hey, one of our foundational reasonings and beliefs is wrong, we can imagine they probably weren't too happy. Now, a lot of historians and a lot of texts say that Hippasus actually, he drowned. And why he drowned, we're not entirely clear on. As I said, the exaggerated stories like to say that he made this discovery on a boat and his colleagues just threw him off for saying something so crazy at the time. And then others say that he actually was potentially sent to death for some other reason that I might cover in a different video, something a little bit more complicated, at least from what I've been reading. So yeah, this is sort of the story of how irrational numbers might have gotten a man killed. Anyways, back to our math proof. In math, oftentimes this example, this very problem, is used as the first problem you solve to introduce to you the concept of a proof by contradiction. Now, before I get into what that actually is, I should probably first explain why we can't prove this directly, because that's the first type of proof you're ever taught. Why can't you use that here? Well, the big problem really arises from the word irrational itself. The word irrational doesn't really have a definition of its own, because its definition depends on another definition. So notice, for example, even is defined as an integer x that can be written as x is equal to 2k for some k that's an integer. And odd similarly is some integer x that can be written as 2k plus 1. These do not really depend on each other. They can exist independently of one another. If you never defined even, you can still prove something as odd. And if you never defined odd, you can always prove whether something is even or not. However, with irrational, we have no working definition for it, but we do have a working definition for rational. So the problem we're really facing here is that rational, we do have something for. irrational, we don't. It's kind of a mystery of how would you define something to be irrational. So, when we're proving something to be irrational, what we argue is that it simply cannot be rational. Something cannot be both rational and irrational at the same time. Now, when we do this, we of course need to know the definition of rational. And what is that? Well, rational is defined as when an integer, for example, x, can be written as x is equal to a over b, where a and b are integers, right? And of course, two more conditions have to be also true for x to be rational. It must be that b cannot be 0, and the last sort of condition it has to meet, it's not really I wouldn't call it a hard condition, I'd call it a softer condition, is that a and b cannot have common prime factors. This is just a fancy way of saying this is the simplest version of the fraction. If you have a fraction a and b, you can't simplify it further. So if you end up writing something like 2 is simply going to be 4 over 2, right? 2 is a rational number. It can be written as a ratio of two integers, 4 and 2, where 2 is not equal to 0. But you preferably would want to write this as 2 over 1, right? You don't want it to have any common prime factors. It's better, it's just mathematically nicer to do it this way. But the reason I call this a softer condition, this third condition, is because realistically this is pretty valid for the most part. So this is what we're going to actually use to prove that the square root of 2 is irrational. We're going to use the definition of rational, which is, again, not something you do in a direct proof. If you want to prove something is even, you use the definition of even. You don't use the definition of odd. But we can't do that with irrational, unfortunately. So that is what I want you to understand as to why we use this weird proof method when it comes to irrational type of problems. So how does a proof by contradiction work, since we can't prove this directly? Well, you could think of it like this. Imagine you are a detective, right? And you need to figure out whether this person, Sam, went to a party, right? But you, as a good detective, assume Sam is innocent. He did not go to that party, right? You say Sam was at home. So what do? You've assumed Sam is innocent and he's at home, but you want to figure out whether Sam actually went to a party. So you investigate and you gather evidence. And in this process of investigating and gathering evidence, maybe you find that Sam took a selfie, right? He took a selfie at, let's say, 9 p.m. at a party, but Sam told you that at 9 p.m. he was at home. But you have physical evidence, the photograph, right? That shows that these two things could not have been true at the same time. And you know for a fact that this photograph is true. So it must be that when you assumed Sam is innocent, you investigated and you found a contradiction in some sort of logic. And what this means is, because this logic shows that he did in fact go to a party, the hard evidence that we know is the truth is that there is this photo, it means that our assumption that he was at home is not correct. And when we say that our assumption was not correct, we say, well, the only other possible conclusion is that he was in fact at the party. This is kind of how a proof by contradiction works. You suppose, for example, the square root of 2 is rational. You then investigate it, or in math you would do some sort of algebra of some kind. And then halfway through your algebra you would notice, hey, something is not adding up with our assumption that square root of 2 is rational, and something in our algebra, and our algebra is definitely correct, and our assumption is just an assumption, it could be right or wrong. So it must be that because this is correct and it doesn't work with the assumption must be false, and the opposite of it must be true. So that is the kind of logic we're going to use to prove that the square root of 2 is in fact irrational. All right, so now let's actually write down this proof. So how is it going to start? Well, first we're going to start by saying, let the square root of 2 be rational, right? We're going to suppose square root of 2, our Sam, is innocent, or in this case, rational. And then we're going to look at this, and as mathematicians, we're going to take a word and we're going to split it up into something we can mathematically use. In this case, we're going to more explicitly say, hey, what does it mean for the square root of 2 to be rational? Well, we can say that then square root of 2, if it's rational, you should be able to write it as a ratio of a and b, where a and b are going to both be integers such that b is not 0 and a and b do not have common or do not share common prime factors, right? So we're assuming it's innocent. What does it mean for it to be innocent? In this case, you could think of this as saying Sam's at home. This is what it means for Sam to be at home. Okay, so next. Well, now let's do some algebra. Let's gather some evidence. So what does that mean in math? It means that we should probably get rid of that square root. Square roots are ugly. We hate working with them. How do we get rid of a square root? Well, you square, right? So what do is we square the square root of 2. So we say the square root of 2 squared is equal to 2, which is going to equal to a over b squared, which is equal to a squared over b squared. Awesome. Next, what do we want to look at? Well, maybe it might be useful to figure out what a squared and b squared are. So maybe let's rearrange for a squared. We can say that then a squared is going to equal to 2 times b squared, right? If we multiply both sides, if we just forget about this middle statement down here and just say 2 is equal to a squared over b squared, if we want to figure out what a squared is, we can rearrange it by multiplying both sides by b squared. And what do we notice here? Well, because b squared is in fact an integer, any integer multiplied by itself is still going to be an integer, so you should recognize that this is an integer. And what do we see? This is 2 times an integer. And what does that look like? Well, if you've seen my even and odd proofs, that's exactly the definition of even. An even integer is simply an integer that can be written as 2 times any other integer. So we can say that, so a squared is even. Fantastic. Where can we go from here? Well, from here you should also maybe go back in my proofs and notice that an even number squared must mean that a is also squared then. Now, maybe I'll prove this as well. I think I only proved the one direction where even squared is even. I should maybe also prove the other direction where if an even number is even, then even squared is even. So, but the point being here is that we can then say, my marker is dying, I might have to switch it halfway through. We can then conclude that a is even because a squared is even. Okay. What does it mean? Well, it means that, therefore, a can be written as 2 times m for some integer m, right? So we're just going to define, once again, another version of even. Great. Where can we go from here? Well, we've argued that this has to be even because b squared is an integer squared and an integer squared is an integer, so 2 times an integer is the definition of even. We've then said, well, if something is squared and that's even, then whatever was squared must have also been even, so we're saying a is even. maybe we can plug A back in here and figure out what B is, right? We've looked at A, now let's look at B. So we can then say with 2 arrows, we can say 2 is going to equal to A squared over B squared, which is going to equal to 2m squared over B squared, which is going to equal to 4m squared over B squared. Now, let's rearrange for B squared. What is that going to look like? Well, when we want to rearrange for B squared, right? Let's remember our high school, maybe even elementary school math classes. We multiply both sides by B squared and then divide both sides by 2. So B squared is going to equal to 4m squared over 2. The 4 and the 2 simplify to simply be 2m squared. So B squared is equal to 2m squared. And what do we notice here? Well, it's very similar to what we had with A squared. M is just an integer. An integer squared is still going to be an integer, and 2 times an integer is our definition of even. So we once again conclude that something else is even. In this case, B squared is even, so B is even. Very similar sort of reasoning as we had with A. Now, let's just take a step back and take a bit of a break. What do we see here? Well, if you've been paying attention, you would have noticed that we've just shown that this rule is broken because A is even and B is even, or hang on, let me actually just say more explicitly, then B can be written as, let's say, 2n for some integer n. Well, what do we notice? We notice that A can be written as 2 times an integer and B can be written as 2 times an integer. They clearly both share a common prime factor, that is 2. 2 is a prime number. So what can we say? We can then say, therefore, to show this even more explicitly to the reader, 2 is equal to 2m squared over 2n squared. And then we can say the square root of 2, if we square both sides, is going to equal to 2m over 2n. And because this clearly isn't the simplest fraction, and it has to be the simplest fraction, it can't be that the square root of 2 is rational, because when we do that and follow the algebra, it breaks one of the fundamental rules for it to be rational. In this case, it does have common prime factors. The A and B are not, in fact, unique to each other. They are multiples of the same number, 2. So we say, since A and B share a common prime factor 2, the square root of 2 cannot be rational. So we've just shown when we say it's rational and follow the steps, we show that it can't be rational because we find that the A and B, the ratio that it can be written as, will share a common prime factor of 2. So we say, by contradiction of square root of 2 being rational, or maybe we shouldn't write that. I'll just say by contradiction, the square root of 2 must be irrational. So there we go. We've just proven by contradiction that, hey, let's assume Sam is innocent. Here's what it means for Sam to be innocent. Then let's investigate Sam. We've investigated Sam and we found, oh, these two things don't add up with Sam being at home. If Sam was at home, this should be true. But clearly we found it's not true. So then we conclude that Sam can't have been at home, so then by contradiction it must be he went to the party. Or in this case, because the square root of 2, when we say it's rational, it breaks the rule of rationality that the ratios of a and b that it can be written as have no common prime factors. We find that it has to have common prime factors because a and b would both be even. So therefore, the square root of 2 cannot be rational, and if it can't be rational, the only thing left for it to be is, in fact, irrational.